So let's continue what we started yesterday. So yeah, yesterday we saw a little bit of a motivation for the study of the work time Fourier transform. And so where did we actually leave things? So yesterday, last time, we ended up discussing the following result by Lee, which is Lee's uncertain principle, which says, so let's just quickly, just a quick reminder of what it says. If I take two functions f and g with delta 1, in a set in R2, where the short time for a transform with window g at f concentrates in L2 norm with level 1 minus epsilon in this set, then the measure of the set has to satisfy the lower bound. And of course, if we optimize on P, then we can actually get that the measure of this set is bounded from below by 2 times 1 minus epsilon squared. Yeah, so that was the last result we showed, which was the consequence of the sharp Hausdorff-Young inequality, the sharp Young convolution inequality. But the remark that we made is that most likely this thing is not sharp. So in particular, the L2 norm of this thing, so that the integral of this whole thing over the whole complex plane, or the entirety of R2, is 1. So this says that actually the mass is really well concentrated on a set. And this is a kind of a Fourier transform, right? That's what the name short time Fourier transform is trying to tell this to us. So its mass shouldn't be concentrated perfectly or nearly perfectly concentrated on a set U, on any set U. And actually there is a way to kind of say that, well, this is very, very much non-sharp in the limit, which is, well, suppose that it concentrates near perfectly on a set of finite measure, then if we could take limits, we would obtain a short time for a transform, which is perfectly concentrated on a set of finite measure. That is, its support has finite measure. But then there's this theorem of Philippe Jamin, who actually said that if I would take two functions f and g in L2, then the support of the short time for a transform with window g of f has finite two-dimensional Lebesgue measure if and only if one of them is 0. So this thing has to spread across across R2. The mass cannot be perfectly concentrated on a set of finite measure. And this is kind of what motivates a slightly more specific definition, which is that of these let's say eigenvalues. You don't know what that is an eigenvalue for yet, but let's say the definition of lambda is 1 of u. And it's just going to be the supremum. So you take the function that best concentrates on a set u, and well, compute the integral over that set on the short time for a transform with window g squared, and divide by the L2 norm of f squared. So this is the lambda 1 of u. And well, one way to rephrase everything that we have asked ourselves so far is, how large can this guy be if the measure of our set is fixed, right? So it's a way to say, well, could we have a sequence, for instance, of sets U such that this measure remains bounded, but these lambda 1s of U converge to 1, which is the upper bound for this? That is an actual question. Yeah, so that is good. So this is just another way, just a different way to state the results that we want to study in this lecture series. So let's maybe start with let's maybe investigate this object a little bit further, right? So the notation is inspired, as I mentioned, by an eigenvalue problem, and as a matter of fact, this is the first eigenvalue of a certain operator, and the operator is what is the so-called time frequency localization operator of U. So what is that? Well, we take short time for a transform applied to F, we multiply it by the indicator function of a set U, and we take the adjoint back. Well, it's not really hard to see that from this definition, this guy is the first eigenvalue. We just need to make sense of the fact that this first eigenvalue indeed exists, right? So we just said, well, it's bounded by one. Well, is there an eigenfunction associated to it? What are the properties of these eigenvalues that we can actually say? And yeah, so just a little bit of heuristics about this operator LU. Just like the original Laplacian encodes information about the set U, so its eigenvalues and eigenfunctions say something about the geometry of the set U. Just for this is an observation by the original Laplacian. The eigenfunctions that satisfy something like this. So this is like the lambda k, such that there is a non-trivial function satisfying these satisfying this PDE, or the spectrum of the Laplacian on the set, and these eigenfunctions associated with that spectrum, they say a lot about the geometry of the set and so on. And just like basically just drawing a parallel between the dirichlet Laplacian and the localization operators, maybe we could say something about the set U from this operator LU. Because, well, as we shall see maybe in the next lecture, if we replace this here by the gradient of F, and this here, but just keep it and take the infimum over F, which are in H1 naught of the set U, we obtain the minimal eigenvalue of the Laplacian on the set U. So there are parallels between these two questions, right? I just wanted to emphasize that before we dive deeper into the tougher properties of this operator. So the first one is that actually this the spectrum of that is well behaved, right? And why is that? Well, the reason is that whenever we have a set U of finite measure, then LU is the Hilbert-Schmidt class of operator. And hence, well, since it's Hilbert-Schmidt, it's compact, and its spectrum is countable and bounded, and hence the first eigenvalue is well defined. It has finite multiplicity, and it is finite. Okay. So how do we prove that? It's actually not too hard. It's going to be a consequence of proving that this operator is actually a trace class, right? And how do we prove that this operator is a trace class? Well, take north and normal basis of L2 and consider these sums. You need to find a sort of a bound for that. And how do we do that? Well, let's just use the definition, right? So these inner products of LU of J with Fj, these are just the integral over U of VGFJ squared dx d omega. We swap the sum and put it inside the did nothing until that point. Well, next we just observed that these guys, one of the ways that we wrote that we were able to write the short time for a transform was exactly like this. So this is in a product of Fj with modulation omega, translation x of the width of G. And now we use that Fj was an orthonormal basis of our underlying space. Since it was an orthonormal basis, this recovers exactly the L2 norm squared of G. So this is a constant. We're integrating a constant over a set U of finite measure. So here we didn't even estimate at all. We just said, well, by the properties of these localization operators, this kind of trace of the operator L is just equal to the measure of U times the L2 measure of G squared. This is finite, hence this whole sum is finite. The operator is trace class implies Hilbert-Schmidt, and hence the operator is compact the spectrum makes sense and so on. Right. But on the other hand, this is kind of as much as we can get for general Windows G. So the general theory for a localization operator is doesn't reach very far at the moment. And it seems that finding the eigenfunctions and eigenvalues is actually like precisely computing them is a challenging problem, even for very simple domains. So the only cases where actually I know that this has been done are when the window is a Hermite function and the set U is a center disk. So in that case, you can show that for instance, let's consider the Gaussian window. That's going to be a recurring theme in this lecture. The Gaussian window is going to be crucial to us. So it's a theorem by Dobeschi that if f is an eigenfunction of the localization operator associated with a center disk, then it is a multiple of a Hermite function. So it's an eigenfunction if and only if actually, and conversely, the Hermite functions, all of them are eigenfunctions of this localization operator. But on the other hand, there doesn't seem to be many sets, at least I can think that in the theory, in the whole theory of localization operators. For instance, if you change U to be instead of a disk, an ellipse, I don't think that it's. I think the problem becomes way harder than it actually than actually the one for the disk. Whereas, for instance, in the case of the Dirichlet Laplacian that we had written on the blackboard, it is relatively simple. An ellipse is just like an affine transformation of the disk, and the Laplacian is a well, you have a different, slightly different operator, slightly different partial differential operator, but you still have kind of a linear PDE to solve, and you can make use of the rich theory behind it in order to find the eigenfunctions and eigenvalues. But here you don't really have, so the window changes, the set changes. If you try to change the set to revert back to kind of a disk, you're going to change the window in a way that you cannot really control. It seems to be a little hard. So in general, these operators are hard to understand, and we should maybe try to focus on the case that we know, which is that of the Gaussian window, but then we might ask what's so special about the Gaussian window. And yeah, so the rest of this talk is going to be basically talking about what's so special about the Gaussian window. And as a matter of fact, it is special because it's connected to analytic functions. Right, so if you take the window to be a standard Gaussian times a constant, then the operator Vg is actually related to what we call the Bargmann-Fock space. Right, so take f in L2. We define its Bargmann transform as this integral right here. It's easy to see that whenever f is in L2 of the real line, then, oh, sorry, this should be a, if I'm not mistaken, this should be like a modulus right here, but, or maybe not. No, I don't think so. In any case, yeah, this actually is an analytic function. It's finite for each z. It's each z in the complex numbers. And if you use Morera's theorem, you can swap the order of integration and show that this actually is an analytic function but just like that, by the fact that these exponentials here are analytic for each fixed line. Right. What's so special about this Bargmann transform that I just introduced? Well, if you take the standard Gaussian window, then the short time for a transform at f of f at x and minus omega is just the Bargmann transform times a Gaussian times a modulating factor. This, of course, will in general be able to ignore this factor here because we want to measure how the absolute value of these guys concentrating on sets of finite measure. So measuring how the absolute value of this guy is concentrating is the same as measuring how analytic functions concentrate on sets of finite measure, right? Due to this proposition. And the proof of this proposition is just basically, well, you know what the Gaussian is, you know what the definition of the short time for the transform of the Gaussian is, you have this formula, you just expand everything, comparing. It's evident that, so let's maybe not bother proving this proposition. And as a side note, whenever we have the standard Gaussian, a different name for this transform is the Gabor transform. Right, so I think this was introduced by Dennis Gabor in the 40s or something like that, in order to analyze problems coming from, I think it was even motivated by physics, so that might have been the reason why Leib was interested in operators at that time. But yeah, so this is the Gabor transform. And from now on, we're going to be mostly focusing in the case of that one. Right, so what are the properties of the Bargmann transform that we just defined? Well, the first of them is that it is an isometry between L2 of the real line and this, what we call the Bargmann Fock, sometimes also called this the Siegel-Bargmann space of analytic functions, which is just, it's gonna be denoted by this F2 of C, which is the set of entire functions such that the L2 norm with respect to this Gaussian is finite. Okay, and then the norm in that set is just going to be like this to the 1/2. And the second interesting property that we're going to be using heavily in this talk is that whenever we take the Hermite functions, then the Bargmann transform of the Hermite functions is just a monomial with a certain normalization factor. Since they're here normalizing the Hermite functions to have L2 norm equal to 1, and this factor just makes the Bargmann Fock norm of these Z to the K be 1. Okay, how do we prove that? So first note that so the proof of this is just a computation as well. So we just use the derivative definition of Hermite functions. It's boring and yeah, I'm also going to skip it. But then the first part it says a metric. It just comes from the Planck-Charles theorem for the short time for a transform, together with the fact that, well, the Bargmann by part 2, the Bargmann transform so the range of the Bargmann transform contains all polynomials, right? So it has to be dense in this class, and you can show that it's an isometry. L2 is a well, it's a Banach space. Therefore, this guy, so the range of this guy has to be the whole Bargmann space. Right. And why is it interesting to us in this particular context? So if we take the localization operator with the Gaussian window, then it has a pretty nice formula when we take Bargmann transform. So if you take f, any function, take the localization operator of f, take the Bargmann transform, evaluate it at the complex number w. Then this is just equal to the integral on the set u of f of z e to the pi z bar w times the Gaussian measure. That's kind of an inner product restricted to u between f and this guy. And the special role of this guy is going to be highlighted soon, as it turned out. So I'm going to give you a couple of spoilers. This Bargmann Fock space that I just defined is actually a reproducing kernel Hilbert space. So point evaluations are bounded. And the reproducing kernel is exactly this guy. So it's so the Bargmann transform of a localization operator is just like a restricted inner product with the reproducing kernel in the set. So this is kind of magic in that regard. Okay, so how do we prove that? The proof is also it's also a bit tedious, but this time I decided not to sweep the whole mass under the rug and then maybe show a couple of details. So let's maybe write this guy explicitly for what it is. So it can be written as an integral on u of d phi. Phi here is going to be the standard Gaussian of f at x minus omega, phi of this guy times this phase parameter, dx d omega. Maybe it's not exactly u, but u tilde. So where u tilde is just you swap, you just reflect U with respect to the y coordinate, but the bottom line is that a formula like that holds. And let phi z of phi of t denote this function. So the action of these translations and modulations at phi for z equals x plus I times omega. Then, well, if we apply the Bergman transform on a function like that, but just recalling the whole, we saw in the last lecture, we saw that the short time for a transform has several very nice properties with respect to the to translations and modulations. So using those in the definition of the Bergman transform, we can get easily that the Bergman transform of this translated and modulated Gaussian is just this guy right here that we claimed it would appear in any case, times the Gaussian factor times this modulating factor. So then we just replace it. So take the Bergman transform here, it's gonna hit just this guy inside. So the Bergman transform of this guy is just this times whatever we had written above. But then we come back and look at what the definition of this was. We had already like this modulating factor times the Bergman transform itself. So the modulating factor kills the modulating factor from this, we get the Bergman transform itself, the reproducing kernel that we're going to see that's the reproducing kernel in that space, times the Gaussian measure, which proves the claim. That's a very I mean, at least I think it's a bit it's extremely nice and magical that this kind of thing happens. That there is such a nice connection between analytic functions, and that here the reproducing kernels are appearing with these localization operators seem to be really encompassing how close you are, and like the best way possible to concentrate on a fixed set. But in order to understand it a little bit better, even let's maybe understand these Fock spaces that we define slightly better. So let's in particular prove that for these spaces, it's a reproducing kernel grid space. So this part is actually a consequence of part 2, which actually is a bound, a pointwise bound on fz squared times the Gaussian by the L2 norm, by the Fock space norm of the function squared. And finally, there's since it's a reproducing kernel grid space, so since point evaluation is a bounded functional, there are kernels K with this property, and we're going to compute these kernels. So let's go for it. Let's prove first 2. Well, how do we do that? You need to prove something like this, that the point evaluation at Z is bounded. And how do you prove that? Well, let's write F as a sum like that, right? It's sum over K of AK times EK of Z, where these guys let's just quickly recall what the EKs were. EK of Z was just applied to the K over K factorial to the 1/2 times Z to the K. And okay, so let's do the most naive thing that we can do, which is just whenever we want to bound f of z, we just take the absolute value inside, right? So this holds trivial. And let's take the second most naive thing that we can do, which is use Cauchy forms. So we get the sum of AK squared and the sum of these EK squared. Now this, we have this formula for EK. If I take absolute values and square it, it's going to be pi to the k over k factorial modulus of z squared to the k. If I sum it over k, I just get this exponential factor. That's plain and simple. And this, the sum of the AK squared, I'm claiming that it's that it's the L2 norm, the Fock space norm of f. So that's it follows by orthogonality, but I think it's instructive to just take a quick look at why. But if we want to compute the norm, this guy squared, well, what was the expansion that's represented this? Like this. and the Gaussian measure. See? That is something like sum for I and j, integral t, ai, aj bar, ek, z, ek, ee, I, or z, ek, z bar. With respect to the Gaussian measure. Right, and these guys are going to be something like, modulo constants. You can take these constants outside. These are going to be some Cij times the integral over C, Z to the I, let J bar, d mu z. Right, but what is this? So we can actually, we use polar coordinates or something like that, and we're going to get this integral from 0 to infinity. And this is going to be r to the I plus j times e to the, let's say, integral from 0 to 5, I times theta, e to the minus j times theta, d theta times e to the minus 5 r squared times r dr. Okay, but this is only non-zero if I equals j. So only the diagonal terms survive. In the diagonal terms, we just said that these guys were constructed so that their Fock space norm was 1. So the sum of the diagonal terms is just sum of the other squared. Okay. So this is just the basic for commonality in the Fock space. If we expand it as a sum of monomials, it's very easy to compute its norm by the L2, the little L2 sum of the coefficients. Right, so what do we get now? So we proved already what we wanted, right? That the point evaluations are bounded, and we proved the part 2 of the theorem of the proposition as a consequence. So now let's prove that this is in fact a reproducing kernel for the space. But then we notice that actually this guy is in the space. It's not too hard to show that this guy for fixed z, this function kwz as a function of w is in the space. This is z in C, not z in big Z. But so how can we actually compute this guy? Well, this expansion here says that all I have to do is take an inner product with the basis ek and multiply it by ek and sum it up in k because of orthogonality in order to get it. Right, but this is a reproducing kernel. So this is just, well, we can swap the order of those and take a bar. And the property that it's a reproducing kernel shows that this reproduces ek at z. So this is ek at z bar times ek at w. But then if we multiply it out, we see that we're going to have a factor of pi to the k over k factorial, z bar to the k times w to the k. When you sum it up, this is exactly the sum of these. This is exactly what the power series definition of the exponential, right? Of this exponential right here. So it just so the proof that this guy is indeed a reproducing kernel of space, it follows directly from what we did so far. Yeah, so that's I think that sums up the properties of the Fock space. And regarding the problem of finding eigenfunctions for our localization operators, we have the following corollary, which is a function f. F in L2 is an eigenfunction of the localization operator if and only if, when I take its Bargman transform, it is an eigenfunction of this projection operator onto the Fock space. And here I'm claiming that this blackboard P denotes the projection onto the Fock space. and that this is equal to this expression right here. And this part, so this last assertion follows from the previous proposition that we showed, that the action of the Bargman transform on L of U was indeed given by this. So we apply, so if f is an eigenfunction of L of U, we apply the Bargman transform on both sides and get this. So the only thing remaining to prove is this part. And we only need to show that this projection onto the Fock space for functions in this L2 of the Gaussian. So these are no longer analytic functions, but they're in the L2 of the Gaussian space. Then the projection is given by that. So in other words, we have to show that for any function in the Fock space, this relationship holds. That defines the projection, right? So this clearly defines a function in the Fock space, this expression, and if you show that this equality holds for any f in the Bargman Fock space, we're good. But then in order to do that, it's actually not so hard. So in order to justify the exchanges, by the way, like in the order of integration, I just think of that as a polynomial or something like that, and then take limits. So if you take PHF, so this inner product, well, what is it? It's just like this double integral that's written right there, right? So if you exchange the order once, we're going to get this integral right here. HZ comes out, and then this Gaussian comes out. But then, well, let's recall what we know about this being the reproducing curve. So this actually just reproduces f at z, but we have a big conjugate on top. So this thing here, this whole integral just equals f of z bar because of what we proved about the reproducing curves. Now we have this thing, which is just h of z times f of z bar with respect to the Gaussian measure, which is exactly what we wanted to show. So we show that it's indeed a projection, and it follows from the reproducing curve property of any function in the Fock space. Right. Okay, so then for the just before we move on, just wanted to highlight again the fact that if we want to understand the properties of the operator L of U, the localization operator with respect to a Gaussian window, then it is crucial to understand functions, analytic functions in the Fock space. It is equivalent to understand functions in the Fock space which satisfy this one. So we just basically translated our whole problem into a problem about analytic functions. And as we know, analytic functions have a lot of structure. We can, we can explore many more properties than the ones that were available to us just a minute ago when the window had no one structure. Right. So let's start with as a warm-up with a proof of the result by Bogashi that the disk has only Hermite functions and multiples thereof as their eigenfunctions of localization operators. Right. So what we need to prove is that if a function f satisfies this property, then it's a Hermite function. Right. But a direct computation shows that this is an eigenfunction, and it's something like this. Well, let's look at what this actually is. We can expand this exponential here. Again, we use this orthogonality that we discussed before. The only term that is going to be remaining after we do this trick once again is going to be the term of order z to the k. And we have something like this. So this integral, the left-hand side, equals z to the k times this guy, which is going to be the eigenvalue. Then we rewrite it in several different ways, right? So it's something like this. So this is going to be the eigenvalue. And we first of all proved that z to the k is an eigenfunction. Since the Bargman transform takes Hermite functions into z to the k, all good. We proved that Hermite functions are eigenfunctions. And in order to prove that they are the only ones, we just need to show that these eigenvalues are strictly decreasing. Because, well, otherwise you could write like an eigenfunction as a power series, right? So let's suppose that we have an eigenfunction f. So something that is satisfying the equation that we want. Then we write f as a sum of, I don't know, ak times e to the k times ek. But then if we apply this operator here, which we call e indicator f, apply this, it's going to be something like e indicator u at f at ek, which is the sum of ak and lambda k and dk, right? So this can only be a multiple of that itself if the lambda k's that appear here are equal. So if they're all, if we show that the lambda k's that are here are all different, then these have to be the only eigenfunctions. And it's not too hard to show that. We just write it as this integral. We integrate by parts once with respect to this guy. We take a derivative onto this aspect here. And we're going to see that explicitly lambda k is just lambda k minus 1 minus this explicit factor, which is strictly less than lambda k minus 1 for any r greater than 0. And hence these guys, z to the I and z to the j, are associated to different eigenvalues, hence they're the only eigenvalues. So with the new language that we found through the Bergman Fox spaces, we were able to show right like Dogashi's result of basically 2 lines. Right. But then let's maybe move for the remaining part of this talk, which is likely a slightly more surprising result. So this result is also already really nice. It links disks, time frequency disks to Hermite functions in a way. But there's an inverse problem associated with that, which is the following. So if I take U to be a simply connected domain, and I suppose that its localization operator has 1. I'm not saying that all the eigenfunctions are Hermite functions. No, I'm saying that only one eigenfunction of that operator is a Hermite function. Then this side is this. It's this is one of my favorite results in this area. It's really cute. It's really short. We're going to see that the proof. It takes almost nothing at all, but it's very powerful as well. I'm just saying that these localization operators are rigid to the point that if one Hermite function is an eigenfunction, then the set is simply connected, and it has to be this. Questions? Okay, so how do we prove that? So let's use what we know so far. So here's the translation for the Bergman transform, right? So what we need to prove is that if this equation is solved, if this equation is satisfied, for all W complex numbers, then U is this. Okay, so we differentiated, I don't know, k times on both sides, right? So we get for a different constant lambda prime that this has to hold for each W and C. And this is actually crucial to us that we're differentiating it because we're creating a different radial weight here. Right? So if we differentiate k times, we drop 5 times that bar. K times, we get a different constant. Doesn't matter to us. We're gonna deduce our result just from this property. Okay, so expand the exponential as we did before. And you see that, well, for any L that I take, this property holds. So this expansion holds. So Z to the 2k times Z bar to the L times the Gaussian. When you integrate that on U, this has to be 0 if L is not 0, and lambda prime otherwise. So just the integral of U with respect to that measure. So, but just like for shortness and notation, take the mu to be this. And now we're going to just suppose that this holds for each L. And some simply connect with U. We're going to conclude that this is a disk. So how do we do that? So the way to do it is with a very nice trick. So let's compute this integral right here. The integral over the set U of modulus of z squared minus z bar times W over z minus W modulus squared against the measure of U. Right? Take W to be an element which is far off from well, it is an element like this. So you have a set U here. This is our set. This is 0. And you take the W is here. It's outside of the ball with radius being the supremum of modulus of z for z, right? This is just technical, so that everything right there is justified. Okay, so what do we get? We get, let's just expand it out. So what is this part of there? So we get integral mu modulus of z squared minus z bar times W over z minus W squared dv of that. Oh, that is just integral of z bar times z minus W over z minus W bar and z minus W, which is just integral z bar minus W bar dv, which is just the first line. And then for the second line, you just divide and multiply by W bar. And I claim that this is 0. Why? Well, because this thing inside can be expanded like this, just summing a geometric series. This thing equals this. And when we exchange the order of summation, which is justified by this thing here, and compute the integral over U of z bar to the end with respect to the measure, and use this property, it vanishes for each coefficient that we have there. So this integral is 0 for any W that we take for this problem. Okay. Next. So by the same idea, we have that this integral equals lambda over W bar. Because right now, when we expand this guy in the power series, we have a 0 order term. Okay. So these are going to be the inequalities that are going to enable our proof, right? So the first observation that we make is that these can be extended. So these identities can be extended for all W in the complement of U. How? Well, notice that this side and this side, so the right hand side here and the left hand side here, makes sense for all W in the complement of U. And here as well. So everything makes sense, everything is integrable, and they define an analytic function in each case. Therefore, by analytic continuation, they have to be the same. They have to agree there. So these identities hold for every W that we for every W that is in the outside setting. Okay, but then let's see how to finish. So the first claim is that 0 is in the set U. Oh, if not, then look at this. Since this formula holds for all W outside of U, this would have to hold for 0. If this holds for 0, then there is a sequence Wn that converges to 0, with this converging to infinity in one. But then we notice that this function is locally integrable on C. Since this is locally integrable on C, these integrals are uniformly bounded on Wn for any Wn going to 0. So this cannot be the case, therefore, and this comes from the fact that we assume that this identity was valid for W equals 0. That cannot hold, hence W has to be, so 0 has to be 0. Okay, Good. Now, take the largest disk that is contained in the closure of U. Right, the largest open disk. Okay, so in that picture that we drew before, we're doing something like this. Let's see, it's here. So this is dr that we're considering, and take W naught to be someone in the intersection, right? So W naught is going to be the intersection of the disk with the disk with the boundary of U. So it's going to be a guy, right? So we use the previous consideration for W naught, right? Or for a sequence tending to W naught. And what do we get? We get that this is just the real part of this integral, which is 0, right? We showed that that integral right there was 0 for each W on the outside of U. On the other hand, we have an estimate for this real part. So this real part in absolute value is at most, well, modulus of Z times modulus of W naught. And W naught is on the intersection of the boundary of the disk with the boundary of U, and hence all Z in the boundary of U have to have norm at least the norm of W naught. It's just this picture right here, right? So the distance to the, if not, if they didn't have the norm, didn't have the norm at least that of W naught, they would be inside the disk, which is a contradiction with the fact that the disk is contained in U. Okay, so this chain of inequality holds, which shows that this integrand is non-negative. So we showed that this whole thing is non-negative, that we're integrating with respect to a radial measure, which has only 1, 0, and 0, by the way, on a set U, yet we found that it is identically 0. So what is the only option that we have? This has to be equal to 0 everywhere, which means that equality here has to hold everywhere, which means that every boundary point of U has to satisfy that its norm equals to the norm of W naught. Hence, every boundary point of U is a boundary point of the disk, which implies that U equals the disk itself. So it's just a very straightforward proof, very clean proof, and as we saw, it uses heavily the machinery from that we built with respect to Fox space and complex analysis, right? So he uses these kind of Cauchy-like transforms that we took with respect to this set U in a very special way. Yeah, so this proves this theorem by Grödel, which is, it shows that disks are already very special because they're the only localization domains of Hermite functions, if we assume everything can be simply connected. And just because I promised that the wavelet transform was making a comeback, I think, well, maybe in the last 5 minutes of this talk, it's good for us to mention what happens in the wavelet world, right? So up to this point, we discussed a lot about the short time Fourier transform, the Gabler transform, and their relationships with analytic functions and all that. What happens is that if you take the wavelet transform with certain windows, which are chosen in a very special way, so they're chosen to be like these monomials times exponentials, and on the Fourier side, so these are called, if I'm not mistaken, Cauchy wavelets. And then the wavelet transforms with the conjugate of those as windows, they are they do yield analytic functions through this relationship. So the function d alpha of f at z is an analytic function on the upper half plane instead of the whole complex plane. Whenever alpha is greater than -1. And this is the so-called Bergman transform. And I think it is completely incidental that there is a Bergman and a Bargman working on the same field. I never really could have I think it's kind of like, it's one of those things that people in the field decided it would be hilarious to have two objects that are related to one another have so similar names. Because I think that one of those, like this Bergman, only like, I think he really did work on his Bergman spaces. But the Bergman might have only worked tangentially with short time for a transform, but they decided, oh, it would be really cool if we actually had almost the same name for these operators. In any case, so
May I make a comment?
yeah,
When there is two Bergman kernel, the second one in complex analysis. He's Polish, I think, and then he moved to US and he started to write his name with one N after some time. And it completely confuses people in complex analysis.
really.
Yeah.
So you see.
Even better.
Yeah, even better. Yeah. In any case. So the Bergman transform of order alpha is just gonna be this operator. You can write it as a certain Fourier transform of something, but let's not just like the Bergman transform itself was not exactly the point of the Bergman transform was not its explicit formula, but rather its property of translating between localization operators or the short time for a transform and complex analysis. The Bergman transform does the same, but right now the complex analysis is not on entire functions, it's just functions analytic on the upper half space. They're gonna be in L2 space with respect to a certain weight. And moreover, if we take a bihomomorphism, identifying the upper half space with a disk, we actually get that studying these wavelet transforms with such windows is actually the same as studying this Bergman space of the disk of that form. So generally for wavelets, the results go through analyzing these spaces, and right now we have basically all the tools that we needed for our analysis. So before in the short time for a transform case, we had to use the fact that things were radial in order to get these orthogonality. We still can get it here, right? So we have a radial weight and we have the disk, so everything works fine in that way. Many of the other features that are present in the case for the short time for a transform, they're present here as well. Of course, you have to do the appropriate modifications, but basically what I want to emphasize here is that as the short time for a transform case, the Gabor transform case, it's kind of the let's say curvature 0 case here, and this is the curvature -1. So this is the problems with respect to the Bergman spaces are generally going to be associated with associating some sort of extremal problem on a hyperbolic on the hyperbolic plane. Whereas in the Gabor transform case, we're working with let's say the flat metric, the usual Euclidean space. And finally, just as a side remark, all the results that we proved here for the short time for the transform, they hold for this for the wavelet transform. For instance, just like Gobeshi's proved that monomials are the only eigenfunctions for disks for center disks in the Gabor case, Gobeshi and Pohl actually showed that the eigenfunctions of center disk with a window of that form that we defined before are still exactly the Hermite functions. And in the same paper, Abreu and Dörfler actually showed that the only wavelet localization domains of Z to the K, and they're, let's say the inverse image of Z to the K under the Bergman transform are the center disks. And the proof is basically the same. It follows the same ideas. So we will not bother with that too much. But let's just take a look at a question that we haven't answered here. So in the beginning of the talk, I said, well, we're going to be trying to answer the question of when this guy's maximal for sets of fixed measure, and I haven't given you. I just said, well, we can prove interesting things about localization operators. But I haven't shown you how to maximize this guy really in this lecture, and that is going to be the main topic of the next lecture. Well, if the flood permits. Yeah, that's it.
Thank you very much. Are there any questions? So could you go through of this algorithm?
Yeah.
So where do we exactly need to assume that this view is simply connected?
Well, it's a good question. I think it is probably right here. Because it could be the case that you, for instance, has a hole. So we use that. Yeah, exactly. It could be an annulus. Annuli, exactly. That's actually saying solve this same thing. So, for instance, this analytic continuation argument only works because the complement of the set U is connected. Otherwise, you could have two different analytic functions. And in order to conclude that the zero is in the domain, you need very strongly. But there is a way to remove it. It's just a paper that I'm trying to finish writing it. You just don't do this proof. You do something different. But it's still in the same lines. But hopefully it will be the other things in life along. I'll write it up soon.
Any other? Yes.
So you said this, you talk more about this trying to maximize the biggest eigenvalue in terms of the sets within the model, but do we know anything about the eigenvalues if we have a given set? So say we have this, for example, do we know how the eigenvalues behave? And are they clustering close to one and have like sort of big decay to zero? Or
That's a good question. I think that there is a couple of papers in that direction. And the answer is yes, given like certain scaling factors of the domain. So if the domain has a certain is kind of large enough, then you can actually prove that there are many eigenvalues clustering and then there's a sharp cutoff. So that basically you can approximate the indicator function of the set well by the first, well, let's say first finite amount of the eigenfunction. But yeah, there's a nice paper by I think it's Calavans-Goeschenig and I think Jose Luis Romero and Abreu.
Okay.
Well, I can send you that later if you want. Which does exactly like that. Is exactly that. It analyzes what they call the spectrogram for this operator.
Okay. The other? Okay, no, then thank you very much for the talk and let me hopefully tomorrow.
Thank you very much.